In this video, we will be looking at the derivative of sine and cosine and even tangent later on. So we're going to start off by graphing the base function sine x, and we're going to try to graph the derivative of the function using our knowledge of tangent lines. So first off, sine begins at the origin, heads up to the maximum, midline, minimum, back to the midline, and I'll continue the same pattern in the other direction. Connect the dots. And here is our sine x function. Now, I'm going to graph the tangent line at the max and mins, because at the max and mins, the tangent lines are horizontal, which means that the derivative at pi over 2, 3 pi over 2, negative pi over 2 should be 0. And now I'm going to think about what's happening in between. Between negative pi over 2 to pi over 2, our function is increasing, which means I'm expecting my function to be here in the positive region. Then from pi over 2 to 3 pi over 2, the function is decreasing, so all the tangent lines will have a negative slope, so I'm expecting things to happen in the negative region. Then back to positive here and positive here. So I'll actually make a little note. Here I'm expecting negative, positive, positive, negative, negative, positive. Just looking at the direction of the function. Is it increasing or decreasing? Now let's see what happens in between negative pi over 2 and pi over 2. So the first tangent line is horizontal. Then as I climb, my horizontal line is going to get a little steeper and steeper. So these are my tangent lines. And then eventually, because I have to reach that next maximum, I'm going to become more shallow until I reach that horizontal line. So I'm expecting to start with a tangent line of 0, like we have right here. Then it's going to increase, and then eventually it has to come back down and become shallow. I just don't know where this is happening. Where is that change happening? At 1, at 2, at 1.5? I do think it's going to be halfway between negative pi over 2 and pi over 2. So what I'm going to do here, I'm going to calculate the instantaneous rate of change like we would have back in advanced functions when x equals 0. So I'm going to calculate IROC equals, so I'm going to take a point very close to 0 to the right and left. So I'll do sine of 0.01 minus sine of negative 0.01 all over 0.01 minus negative 0.01. And if you punch this into your calculator, you get 0.99 and so on. So it's a value very close to 1. If I try using 0.001, then I'll get even closer to 1. So with that in mind, I'm going to put a maximum right here. Now I'm expecting the same idea to happen when the function's going downwards, but at pi, instead of a slope of 1, it'll be a slope of negative 1. And here we are. Now we can kind of continue that pattern. And now if you look at the derivative of sine x, the red line, it just looks like cos x. So that's what the derivative is. If f at x is equal to sine x, the derivative f prime is cos x. And we can apply this to the chain rule as well. You're not always just going to have sine x. You might have sine of another function, like sine of x squared, sine of 4x, sine of the square root of x, whatever it might be. So with chain rule, it was always take the derivative of the outside function, keep the inside the same, then multiply that by the derivative of the inside. So if I have sine of g of x, my outside function is sine, So first I'm just going to take the derivative of sine, which is cos, and I'm going to keep the inside function the same. And then my inside function is g of x, so I have to multiply what I just wrote by the derivative of g of x. And there it is. Let's try the same thing a little faster for cos x. Apologies, little typo here. We're going to graph y equals cos x. So we're going to start with the maximum and head down and do our nice periodic wave. Now again, where I have those max and mins, that's where I'm expecting my derivative to be equal to 0. So I'll plot all of those points in red. And because sine and cos are the same shape, just a shift apart, I'm expecting the same thing to happen. So from negative pi to pi, we are increasing here. So I'm expecting the derivative to be positive. And it'll go something like this. Then the function decreases. So the slope of the tangent line should be negative. And then it increases again. And now if you look at this red function, it's starting at the midline, at the origin, but then it's heading downwards. So it's a sine function that has been reflected. So the derivative of cos x is negative sine x. And again, with a chain rule here, if cos is my outside function, the first thing I'm going to do is take a derivative of cos, keeping the inside the same. And then it's time to take the derivative of the outside and just multiply that with what we already had. And there we have it. So let's try a few examples, and then we'll add on the derivative of tan. So we're going to start with f at x equals sine of 4x. This is a chain rule. Our outside function is sine of something, and the inside function is the 4x. So when we take the derivative, we're going to take the derivative of the outside first. So the derivative of sine is cos, and I'm going to keep the inside the same, not touching that. And once I've done that, now I can go into the inside function, and the derivative of 4x is 4. Now you can keep it like this, but this is really just cos of 4x times 4. We can bring the 4 and just write it in front. It might just make things nicer if I had to do any solving later on. And it's just important that you don't accidentally multiply the 4x with the 4, because 4x is part of cos. It's like the theta of cos. Instead of cos theta, we have cos of 4x. Okay, next one. G of x is cos of 3x squared minus 4x. Again, we have a chain rule here. So I'm going to take the derivative of my outside function first. And the derivative of cos is a negative sine. And I'm going to copy paste the inside function. I am not touching that yet. And now it's time to take the derivative of the inside function, which is 6x minus 4. Next one, sine x squared plus cos of 4x. So again, we have two chain rules here. Just a note, when you see sine x squared, that exponent of 2 applies to the x only. So if you wanted to add a set of brackets around the x squared, you're more than welcome to. If I wanted it to be sine x all to the power of 2, I would need to show either brackets around sine x or put the exponent of 2 above sine. So sine squared x, kind of like here. This means cos x all squared. All right, let's take a derivative. We're going to start with the derivative of sine x squared. So we have a chain rule here. The derivative of sine is cos. I'm going to copy paste the inside function. Now I'm going to multiply by the derivative of the inside. That function is done. Next, cos of 4x. The derivative of cos is negative sine, so I'm actually going to write minus sine instead of plus. And then copy paste the inside function. And now it's time to take the derivative of that inside, which is 4. Okay? An extra step you can do here, just so that you don't accidentally multiply the angle part with those inside derivatives. take the 2x, put it out front. Take the 4, bring it out front. So 2x times cos x squared minus 4 times sine of 4x. And there we have it. Okay. Next one, no chain rule here because the angle part is just an x. It's not a fancier function, but we do have a product rule. So product rule says take the derivative of your first function, which is x. The derivative of x is 1. And then multiply it by your second function, which is cos x, plus, now take the derivative of your second function, and the derivative of cos x is negative sine x. So I'll actually just write minus sine x, and then multiply that by the original first function. Now just to clean up here, I'm going to bring that x in front of the sine x. Again, I don't want people to accidentally do x times x and write x squared, because that would be wrong. This is technically sine x is its own thing times x. All right, moving on to the derivative of tan. Now, we're going to come up with this derivative together because we know tan is sine x over cos x. So we just have a little quotient rule here. So let's go ahead and do that. The quotient rule says take the derivative of the numerator. So the derivative of sine is cos x. Now copy paste your denominator. So there's another cos x. Minus, take the derivative of the denominator. The derivative of cos x is negative sine x. And copy paste your numerator. All over the denominator squared. Okay, and yes, you could write cos x all squared like this, but it's more typically seen as cos squared x, as we saw in advanced functions and maybe 11U. All right, clean up time. Cos x times cos x is cos squared x. Two negatives make a positive. Sine x times sine x is sine squared x. And now I see the Pythagorean identity on top. Cos squared x plus sine squared x is 1. And 1 over cos squared x, thinking of your reciprocal identities, is secant squared x. And there we are. The derivative of tan x is secant squared x. Now, if you remember, this makes life easier, but if you ever forget the derivative of tan, you can always recreate it for yourself on the spot. All right, on to the next. J of x is equal to cos squared x. It might be helpful just for visualization to write this as cos x squared. We do have a chain rule here, but the outside function is the fact that we have something to the power of 2. So when I do my derivative, I'm going to deal with something to the power of 2 first. And how do we take the derivative of that? Bring the 2 down, copy paste the inside. Now it's to the power of 1. Then I can take the derivative of my inside function. The derivative of cos x is negative sine x. And then I'll just clean this up. I'll bring the negative out front, so just negative 2. And then cos x sine x or sine x cos x, it doesn't matter. I kind of like writing sine x first. And now when I see this, 2 sine x cos x, maybe it reminds you of the double angle identity for sine. So we could also write this as sine of 2x. Optional. I mean, if I had to do any solving, maybe I like this form better, but I just wanted to show both versions. And there it is. Okay. So as you can see here, we're just practicing applying sine and cos to all of our other rules that we already know. We'll do a little solving question in a bit, but let's look at some fancier derivatives. Tan of 1 plus x cubed. So another chain rule here. Our outside function is tan. We just found that the derivative of tan is secant squared. Keep the inside the same. Don't accidentally take the derivative of the inside right away. Okay? And now chain rule, the inside function, the derivative is 3x squared. There it is. Next one, p prime. Feel free to pause the video and try these last ones on your own, taking them slowly, and then coming back to check your work. Okay, so here I have sine x plus cos of 3x all to the power of 4. So I have a few chain rules in here. The first is the fact that I have something to the power of 4, which means bring the 4 down, copy paste the inside, now it's to the power of 3. So that's us doing the outside. Now time to do the inside function, which is everything in the bracket. The derivative of sine x is cos x, and the derivative of cos of 3x, another little chain rule here, the outside is the cos, the inside is the 3x. So the derivative of cos x is negative sine x. Keep the inside the same temporarily, and now multiply by the derivative of the inside. And there we are. I could bring that 3 out front just for cleaning up, but here, just practicing that derivative skill. So I'm just going to keep this first step. Okay, final one. We have cos of 3x all to the power of 4 plus tan squared of x squared minus 4. And again, it might be easier to visualize this as cos of 3x all to the power of 4. So your outside function is something to the power of 4 plus tan of x squared minus 4 all to the power of 2. So we have a chain rule within a chain rule twice. So let's give this a try slowly. First thing, I'm going to deal with that 4. 4 something power of 3. That something is the inside. Now it's time to take the derivative of the inside. So the derivative of cos is negative sine. Keep the 3x, and now multiply that by 3. There's the first portion, and we'll go on to the second in a minute. Now when I look at this, there are a few things I would clean up. The 4 is a coefficient, the negative or the negative 1 is a coefficient, and so is the 3. So those I would just multiply and write them as a nice negative 12 out front. Then we have cos cubed of 3x, or you can write cos of 3x all to the power of 3, doesn't matter. And then sine of 3x. There's the cleaned up version. Now the final piece here, we're going to deal with the exponent of 2 first. So bring the 2 down, copy paste to the power of 1. Now time to take the derivative of the inside function. The inside function is tan of x squared minus 4. The derivative of tan is secant squared. Copy paste the angle part. Now let's multiply by the inside derivative, which is just the 2x. Now in terms of cleaning up here, I would multiply the 2 and the 2x to bring them out front. So just 4x, then tan of x squared minus 4, and secant squared of x squared minus 4. And there we are. A longer derivative wouldn't do anything with this, to be honest. We wouldn't be solving for x in a very extreme equation like this, but practicing the skill, keeping track of what part of the chain rule you're on, making sure you're taking the derivative at the right time. All right. And final question here. We are going to determine the x values of the function f at x equals sine of 2x, where the tangent lines are parallel to the line x plus y minus 6 equals 0 for the interval 0 to 2 pi. So just before I take any derivatives, I'm just going to isolate for y here. And we want to be parallel, or we want our tangent lines to be parallel, which means we're looking for a slope of -1. Or we're looking for the derivative, so that general expression for all of the slope of the tangent lines to be -1. So let's find that derivative. We have sine of 2x, so just a little chain rule here. The derivative of sine is cos, keep the 2x, And now multiply by the derivative of the inside. And now let's set our derivative equal to -1. And now we just have a typical trig equation that we have to solve. So I'm going to divide both sides by 2. And now I'm going to think of my special triangles. I'm going to think of alpha, the cast rule. So in terms of my special triangles, we know there's one that's 1, 2, √3. This angle here is 60 degrees, or pi over 3. This one is 30, or pi over 6. And we want adjacent to be 1, hypotenuse to be 2. So our alpha must be pi over 3. And we're dealing with cos here, and we were given a negative ratio, and cos is negative in quadrants 2 and 3. So let's find those angles. Now, just note here, our angle isn't a clean x or theta. Our angle is 2x, so it's not that theta is equal to a particular angle. It's that 2x is equal to a particular angle. So in quadrant 2, we're doing pi minus pi over 3, which is 2 pi over 3. And in quadrant 3, we're doing pi plus pi over 3, which is 4 pi over 3. And now we do need to solve for x here, not 2x. So I'm going to divide both sides by 2 or multiply by a half. I think seeing it as multiplying by a half is a little better. Times a half, because then I see, oh, 2's cancel out. And I'm left with pi over 3 as one of my answers, and it is within the interval, so that's good. And then again, multiply by a half or divide by 2, whatever. And here I can see I can reduce the 4 over 2. And x equals 2 pi over 3, also part of my interval. But now when I look at these angles, I see, oh, these are quadrant 1 and 2 angles. Maybe there's more because I'm allowed to go all the way to 2 pi. Now, our angle was 2x, meaning the k value was 2. And we know that affects the period of the function. So I can calculate my period quickly with a 2 pi over 2. And I see that this cycle repeats every pi. So I can add pi on to get potentially more places where the tangent line is parallel to that particular line. So when I do pi over 3 plus pi, I have 4 pi over 3. That works. And 2 pi over 3 plus pi is 5 pi over 3. That works. So we have 3 answers. If I try to keep adding pi, I will go beyond the 2 pi, so I will stop here. And those are the x values of the function f at x equals sine of 2x, where the tangent lines are parallel to x plus y minus 6. And that's it for our derivatives of sine and cos. And all the previous types of questions we had, like find the equation of a tangent line, find the max and mins, like an optimization style question, can apply to these sinusoidal functions as well.